right, so welcome everybody to today's Quasi World. Our first speaker here today is Carolyn Davis, and she will tell us about Alice in Quasi World. Please, Carolyn.
Thank you so much, Mario and Nina, for the invitation to speak. I wanted to share with you some work that I've been doing recently in the pure N varieties, and I wanted to present it in a story that is reminiscent of Alice in Wonderland. So why don't we just get in it? Of course, if you have any questions at any point, please interrupt. So the story begins where Alice is reading a textbook about the pure N0 varieties, and we're always going to be in the space of quadratic rational maps. And quadratic rational maps always have two critical points that you can use up to conjugation to put them at 0 and infinity, where you can have a form that looks like this. And what these pure N0 varieties are is that they're these quadratic rational maps where you take a critical point and you mark it to be in an N cycle. So this is really an arithmetic condition where we impose infinity to be in an N cycle, but then our other critical point of 0 is free. So if all of quadratic rational maps have a two-dimensional moduli space in the sense that I have two different parameters of complex dimension 1 that I can each modulate, then each one of these varieties becomes one complex dimensional because I have one dimension that I can adjust. So to give some examples about why these are arithmetic conditions, we can look at some examples for imposing infinity, which will always put our marked N cycle at infinity. If infinity is fixed, then we have a polynomial because it's a critical point and it's fully ramified. Then this means we're the form z squared plus a, and our free critical point just maps 0, goes to a squared plus a, etc. And this generates a pure 1, 0, which is you may be familiar with if you've seen the Mandelbrot set at all. And these arithmetic conditions can be used to define a set of Gleason polynomials, which is somewhat relevant that we'll mention in a second. If you prescribe infinity to now be in a 2 cycle, you can check that where infinity maps under this form, that infinity maps critically to the point 1, because that's what 1 over 1 is. And then 1 maps back to infinity, because 1 squared minus 1 is equal to infinity. And then 0 does whatever it does. It maps to minus a, maps to a squared plus a over a squared minus 1, and et cetera, et cetera. And if you wanted to play this game for general M, the goal is that you would use this functional equation and you would prescribe the behavior of infinity under this. So infinity would map to 1 always, and then 1 maps to 1 plus a over 1 plus b. Of course, we're agnostic about 1 plus what a and b, of course, are. But then these would map to 1 plus a. I'm not going to try to read that whole equation, but we can just call that x3, and so on and so forth. And at each step, we'll get this xn. And pure N0 will be the set such that a or b, such that xn is equal to infinity. And then you want to make sure that it's not in a lower dimensional, like you don't want like xn over 2 to be infinity. And so it's periodic of n over 2. So this is at heart, this defines just some variety, just some relationship between a and b parameters that satisfy this behavior. Because for each a and b that it does have xn being the first iterate of infinity, that is infinity to itself, infinity is in a critical N cycle. So in that sense, it is just a dynamical subvariety of QRM. And it's been an open problem for the last 30 or 40 years to determine whether or not pure N is irreducible, meaning these equations of a and b, over the complex numbers. And with a bit of massaging of definitions that may be more familiar to algebraists, this equivalent to pure N being smooth and connected. Epstein proved that pure N0 is in fact smooth. So to show that pure N0 is irreducible, it suffices to show that it is connected. Some other recent progress towards this was by Rohini Ramadas at MSRI. And she showed that these pure N0 curves are irreducible over C, insofar as these Gleason polynomials, which were the analog ones over pure 1 to determine the centers of the hyperbolic components of period n, the Mandelbrot set, if those are irreducible. The virtue of doing that is that those curves are much simpler. They don't have singularities on them, and computers can verify them much easier. And computers did for about n less than 20. But still, for the general case, there's really not Eisenstein doesn't work to show that the Gleason polynomials are irreducible. And at that point, that's pretty much like the only thing I know how to do to show that something is irreducible. So this brings us to our story about Alice in Wonderland. Now, if you have read Alice in Wonderland, the first chapter begins with Alice reading a book, and she was getting very tired. And there's this quote that I very much really like that says, "She peeped into the book her sister was reading, but it had no pictures or conversations in it. And what is the use of a book," thought Alice, "without pictures or conversations?" So when Alice will go explore all these pure end curves, we'll do so with lots of pictures. And after the talk, maybe if you have a suggestion about how to incorporate conversations into a talk, I would be happy to hear that. Okay, so let's say that Alice lives in Pier 1, 0. More specifically, she's going to live in the Mandelbrot set, which is the non-escaping set. This is maybe like the land, and then the complement of the Mandelbrot set is maybe like some ocean or something. And the non-escaping set, or the Mandelbrot set, is defined as all of the parameters of Pier 1, 0. So Pier 1, 0 itself is just a plane, but the Mandelbrot set inside of the plane is all of the parameters, such that when I iterate my map, my free critical point does not tend towards infinity. And we can define non-escaping sets for higher pure end curves very similarly. So our story begins with Alice coming out of the basilica, and she notices a rabbit. And the rabbit itself was maybe not terribly interesting, but then she notices as the rabbit runs away, it begins to grow in ears. And she finds that rather curious, so she chases after the rabbit. And as the rabbit runs and runs away, eventually the rabbit becomes through a valley of elephants and ultimately disappears into a rabbit hole. Alice chases, and then she emerged in a new space. At first, Alice doesn't notice that she's in a new space because at the end of the day, she just sees that there are elephants, just like there were in her home in the Mandelbrot set. But then when she looks to the left, she notices that there's a puncture. And there's nothing in Pier 1, 0 that has anything like a puncture. So she finds this very, very curious. She finds a piece of cake that says, "Eat me." And when she does, she grows was very large and is sitting at the top of her variety next to infinity, so she can see all of the global structure all at once. The curve that she is looking at is Pier 2, 0. So I can tell you now that the goals of the talk, now that we've talked about this, the goals of the talk is I want to introduce you to Pier N 0 to show you the structure from the inside. And there are two particular things that I would like to show you. The first is large scale themes that relate how to organize the non-escaping set and the global variety itself by using the combinatorics of polynomials. And I also, how this relates to themes like connectivity, and modeling our mating locus, or modeling our non-escaping set. And then after that, Alice is going to drink a vial that's going to make her go really, really small, and she'll explore small scale themes. And this will be a chance that I'd like to explain a theorem joint with Alex Capiamba that explains an asymptotic similarity between a neighborhood of the puncture in Pier N, so this guy right here where you see the elephants, and a neighborhood of a parabolic in a simpler Pier N curve, or pre-periodic curve, such as the Mandelbrot set, elephants over here, to explain these pictures. So that's the talk goals. But first, let's start with some observations that we have about the non-escaping set in Pier 2 itself. The first thing that we might notice is that there are lots of small Mandelbrot sets inside of this curve. And this is explained by a classic phenomenon like renormalization that you may be familiar with. The Mandelbrot set is Universal paper by Kurt McMullen. But then you'll also notice that there's this really big prominent Mandelbrot set looking thing, but I like to call a Mandelfold because it's locally a Mandelbrot set. And it's not quite an exact copy because it has two cusps instead of one, and it's somehow missing a 1/2 limb. So if you're familiar with the Mandelbrot set, you'd see that it looks like this. We're actually going to rotate our Mandelbrot set just because of the parameterization. And every point in the Mandelbrot set is special because it is encoding with combinatorial information about where it is. Every polynomial in particular is in a limb. The limb is the unique rational number P over Q that is the rotation number around its fixed point, and is also denoted by these P over Qs right here. So this would be the 1/4 limb, the 1/3 limb, the 2/5 limb, the 1/2 limb. And we can see a lot of this structure in M2. We can see that there is the 1/4 limb, the 1/3 limb, the 2/5 limb, but we'll see that there is not actually a 1/2 limb. So the 1/2 limb seems to be actually replaced by a puncture, and it's something mysterious that is to be explained. And the third thing is that where the complement of the Mandelbrot set is a disk, the complement of the non-escaping set in Pier 2 has infinitely many different components, and they seem to have some intricate touching structure. And that's also something to explain. Okay. So chapter 2 in Alice in Wonderland is Pool of Tears, but if you pronounce it like tears, you can introduce 2 surgeries which explain these different phenomena. Ultimately, these surgeries will be ways of getting rational maps from polynomials, which will help us do things like organize our non-escaping set. The first such tool is that of polynomial matings. Every polynomial that is locally connected, and if f is post-critically finite, like our maps are, then that satisfies this hypothesis, come equipped with something called a Butcher coordinate, which is a semi-conjugacy on the complement of the Julia set to the angle doubling map that extends to the actual Julia set. And this allows you to take radial lines and import them to land somewhere on the actual Julia set. And then the images under these lines under angle doubling is reflected in these external rays, as we call them, landing in the actual Julia set. So it's a way to combinatorially understand our very complicated fractal images by pulling them apart with a semi-conjugacy to a circle and then understanding circle doubling there by just angles. So if we have 2 such polynomials, the way that we can mate them is by gluing the external rays of one onto negative the external ray of the other. This is kind of like the Coriolis effect, why, like your drain will flush counterclockwise if you went to the southern hemisphere. So as an example, we can look at the basilica mate rabbit over here. And we have the basilica rays. It starts off as 1/3, but then once I cross the equator, this ray becomes 2/3, and I see what the landing point of the 2/3 ray is on the rabbit down here. And then these are in a ray equivalence class, and I would do that for all of my angles. And then once I have this, I will then quotient out by all of my rays, and I will get something, if it is a rational map, which we'll talk about in just a second, that is called the mating. And I would like to show you some videos from Sherry Ta about slow mating as a way to visualize this. And if you guys really insisted, I would skip the rest of the talk and just just play these videos. So this is just this example we just talked about the basilica and the rabbit. So and they have the external rays dragged in. And what Sherry Ta is implementing is a way of dragging these fractals together by collapsing down these rays. And you should maybe be following around these lines to see how they're shrinking. Yeah, so, and then what you get now is the mating of the basilica and the rabbit, where they now have a common Julia set, which is the image of both the basilica's Julia set and the rabbit's Julia set. In general, this can be a very, very complicated phenomena, and I know a lot of you who come here are interested in Sierpinski carpets, and this can be a large source of from matings as well. So this is the mating of 2 different polynomials that have a lot of stick in their Julia set, such that when we glue them together, they'll give us a shape that you may find familiar. This turns out to be an actual Sierpinski carpet, and we'll talk about some of the difficulties about how this, what that implies for in parameter space soon. So I just want to pause there. Does anyone have any questions about the mating procedure or anything else along that lines? Everyone okay? Okay. But a priori, what we did is that we did some surgery where we glued together 2 fractals. There's no reason to expect that this actually comes from the Julia set of a rational map. And this is what Tonley, Shishikura, and Mary Reese show in their mating theorem, that shows that for 2 polynomials, that the mating exists if and only if these maps are in non-conjugate limbs. This is to say that if your two polynomials' rotation numbers don't add up to 1 at their fixed points. So if you're in the 1/3 limb, your conjugate limb would be the 2/3 limb down there. And any mating you would do between any polynomials in here and in here would be obstructed. You can't mate F and G if they're both in the 1/2 limb, but you could mate F if it's in the 1/2 limb and G if it's in the 1/3 limb. This will become relevant for the last part of the talk. When F and G are in conjugate limbs, so maybe F and G are both in the 1/2 limb, when you do this mating procedure, the reason that this fails to be a rational map is that we get a Levy cycle in the sense that pinches off our curve when we pinch all of our curves together, and we degenerate from a sphere to a wedge of spheres. And if you can imagine this is this mating of the basilica in itself, where we have the rays that we just looked like, but this time they form a loop right here. And you can imagine that when you pull that tight, when you pull a belt really tight on a sphere, that gives you a wedge of spheres. And you can't really do rational maps on a wedge of spheres, or can you? Stay tuned for the end of the talk. The interpretation of this is that we can think about the Mandelbrot set as all of the ways to deform a fixed critical point. So if the central component of the Mandelbrot set has the map z squared, we can think about z squared as being a mating of z squared with itself. So we have one critical fixed point coming from infinity. This is why we're in the variety pier 1, 0. But then this center component is the simplest one because it's saying that our free critical point is also a fixed simple critical point. And then the Mandelbrot set represents a sort of space of directions of deformations that we can do. So for instance, if we were to bifurcate our free critical point, that would mean that we could change our fixed critical point to a critical 2 cycle if we were to go to the basilica, perhaps. And the Mandelbrot set represents all the different possible ways that you can deform your fixed critical point and still not have it tend to infinity. Of course, in general, the maps F mate G and G mate F are the same in RAT2, right? But our space of pure N has a particular marking. So if I were to do, this is Z squared mate Z squared minus 1. If I were to flip this around and downstairs do Z squared minus 1 and mate Z squared down here, these are different markings for our map. So they're not considered the same in these pure N curves. Okay, this is kind of a subtle point that's important, that in general, F mate G is not the same as G mate F when you're looking in the context of your pure N curves. So insofar as we're looking in pure 2, and we have now infinity is in a 2 cycle, the simplest such map is having the other free critical point be simple fixed critical point. But then we can appeal to, like, what is the Mandelbrot set, right? What is the Mandelbrot set is that you can deform this simple fixed critical point however you would like, except for the Tonley mating theorem tells you that if you were to deform it into the 1/2 limb direction, if you were to have a rotation number 1/2 around the fixed point under a potential deformation, that would give you something that would be an obstruction. And this is where we get our puncture right here. So this is like this very natural way of trying to think about the mating locus of the basilica as something that should look like Mandelbrot-y, but there should also be a puncture, and that explains why we would see that upstairs. The next recipe is to talk about polynomial captures. And I'm going to say a polynomial captures that you begin with a polynomial f and a pre-periodic component k. So it can be pre-periodic or it can actually just be periodic, either one. And I'm going to denote this f plus or minus k because sometimes you have 2 rational maps that you can get from this, but also a lot of the times you only get 1. But what the procedure looks like is, in this case, we'll take f to be equal to z squared minus 1, our basilica. And we'll take k to be this for 2 component right here. And the basilica has the 2 cycle, 0 maps critically to minus 1, and then minus 1 maps back to 0. Now this this for 2 component k is pre-periodic, so it maps into the cycle. And what the capture procedure is that we look at its 2 inverse images. So there's a y plus that maps onto 1, and there's a y minus that also maps onto 1 over here. So we'll look then at the inverse image and label it y minus and y plus. And then we'll choose a gamma that's a path that matters up to homotopy relative to the Hubbard tree, which is right here. So this is actually homotopic to this over here because we don't care about infinity. So we choose a path gamma that connects y minus and y plus, and then we're going to get an invariant graph when we quotient out by gamma. When we quotient out by gamma, this identifies this point y minus to this point y plus. These were both the preimages of y, so these both map here. So this means we've artificially turned y into a critical value because its two preimages have been manually smushed together into a critical point. Of course, this is a surgery. There's no reason to expect this is to actually be a rational map. But when we have this forward invariant graph, we can extend it uniquely to a branch self-cover of the sphere. And then we can check if it is equivalent to a rational map. And when it does, it will obey the combinatorics of this pre-periodic two component, where this component maps here this is our critical point, mapping here, maps up to the other critical point, and then is in a two cycle. But then the question is, when can you actually get a rational map from this procedure at the end of the day? The theorem of Whitner and Luo shows that you can capture out of a two component K, and that this is actually equivalent to a rational map if and only if your pre-periodic component is not in the sector of the alpha fixed point that contains the critical value. So if in our basilica, our alpha fixed point was right here, if we were to delete our alpha fixed point, that disconnects our Julia set because it's a tree. And we have several components, 2 in this case. And if this sector of the alpha fixed point containing V is the connected component of the Julia set minus the alpha fixed point that contains the critical value. So that's this entire side. And if you do that, there's a Levy cycle you can find not too difficultly. And if you do try to do a capture on this other side, it's a little bit more intricate, but you can show that it's actually unobstructed. And the real impetus for using this is that if matings helped see what the Mandelbrot set looked like, these captures are telling you how the basilica geometry shows up in Pier 2. And that is through a thing called bubble rays, which shows that this really complicated touching structure of Pier 2 minus M2 is actually homeomorphic to a partial basilica. And I say partial basilica because I mean we need to throw away the entirety of this sector of the alpha fixed point containing the critical value because you can't do captures there. So if I only take this part of the basilica, then these correspond to capture components in Pier 2. So this one would correspond to here, and then this hyperbolic component is touching this hyperbolic component in the same way that this Fatou component is touching this Fatou component. And in fact, that touching structure is preserved under this operation. Okay. Okay. Then putting this all together, Whitner originally conjectured this, and then later Luo and Dudko proved this, is that when you put both of these together, if you were to actually mate this partial basilica and this partial Mandelbrot set, so you have to delete both things so everything is meaningful at every given point. So you can't take anything over here because those captures are obstructed, and you can't take the 1/2 limb because those matings are obstructed. But then if you mate together this partial basilica and this partial Mandelbrot set, you get something that's homeomorphic to Pier 2, 0. Dynamically meaningful so as well. And this is kind of like the gold standard, I guess, for organizing your variety, because you can reduce it to a mating of the Mandelbrot set, which you understand, and a polynomial, which you completely understand. The other thing that is worth mentioning is that the Mandelbrot set has these veins. You would hope to see that these veins actually exist in Pier 2, because this is like very fine additional combinatorial structure. And in fact, the bubble rays are enough to show that the veins actually exist, but we'll see in higher varieties how this can be a problem. Okay. Okay, so at this point, Alice has been growing steadily this whole time. She's been going into the puncture. She ate this cake. She's getting so big and big and big. Eventually, she goes up past infinity and arises in a new variety.
So a quick question.
Yes.
So would you say that this somehow gives a complete understanding of this per two set?
It shows that you have the combinatorial raised of how to organize all your hyperbolic components, and you have these veins. But in Dima's paper, he was also trying to prove independently that the M2 non-escaping set is locally connected, independent of whether or not the Mandelbrot set is locally connected. There's actually an issue with the argument there. But I think the only other question you might really be interested in is like local connectivity of this. But insofar as you believe local connectivity, I think, yeah, that's probably most of the things you would hope to worry about. But of course, it's math. So it's just like with anything, you can find more questions to ask about. But yeah, again, this idea about finding a global lamination. So on one side, I have like the basilica lamination. On the other side, I have the quadratic minor lamination. And representing a variety as a quotient of that, I think, is like the gold standard for understanding something combinatorially. But yeah, thank you so much for the question. So Alice keeps on growing and growing, and she eventually goes up past infinity, and she emerges small in a new variety. And again, at first she thinks maybe I'm just in the same place because I still see elephants. She knows she's not in Pier 1 because when she looks to the left, she sees another puncture. But when she looks around the puncture, she sees more elephants on the other side. And that's not like something that she saw in Pier 1 or in Pier 2. And when she keeps growing and she finds herself near infinity again, she finds herself looking at a new variety. This variety is Pier 3,0, and it has a new non-escaping set inside of there. But of course, it's chapter 3. It's the Mad Tea Party. So Alice is invited to the Mad Hatter, who lives in the airplane's mating component. But how can she get there if she emerged from over here? Okay. Of course, if you just look at Pier 3,0, you can still see that there are many small Mandelbrot sets that are explained by renormalization. But now you see that there are 3 sort of distorted components that have punctures. You have a component that corresponds to the rabbit, the co-rabbit, and the airplane. And in general, in Pier N, for each polynomial component, you'll have a mating locus associated to that has a puncture attached to it. So this is kind of how you can look your way around. So she's over here, and the Mad Hatter is over here. She needs to get to his tea party. How can she get over there? This is really a question of whether or not M3 is connected or not. So now we can turn our attention to this question of connectivity. And recall that from the introduction, due to the work of Adam Epstein, connectivity does imply the irreducibility of these PRN0 curves. The first thing to note is that why is M3 connected? Well, you can show I'm only saying a proposition rather than a theorem, because I think a lot of the heavy lifting was done through some work of Milner that shows how hyperbolic components are disks. You can show that if Pier N is connected, then this implies that the non-escaping set inside of it also has to be connected. And that if it weren't connected, you have to have a hyperbolic component that is not simply connected, and Milner can rule this out. So the question still becomes, is Pier N connected? Which again is asking, is it irreducible? And this is a hard question. The fact from Milner, though, is that every connected component of Pier N contains a polynomial. So in Pier 3, there are 3 polynomials. There's the rabbit, the co-rabbit, and the airplane. So there's at most 3 connected components. So how do you show that 3 connected components are actually one connected component? Well, you find a path from one connected component to another. So if we can just find a path from the rabbit to the airplane and the co-rabbit to the airplane, then we'd be done in showing that this is connected. So in other words, Alice needs to find her path to the Mad Hatter Tea Party. But how is she going to do this is that we're going to exploit these things that are called shared matings. What this is saying is you can have a mating that is in the mating locus of both polynomials. So this particular polynomial, the rabbit mate the airplane. So if you start in the rabbit component and then you bifurcate your free critical point towards the airplane, this is unobstructed because they have different non-conjugate rotation numbers. It turns out that this is a coincidence that this is also equal to the airplane mate the rabbit, meaning if I were to start at the airplane and bifurcate my free critical point to the rabbit, I get the same rational map with the same marking, in fact. And so this is a special phenomenon that shows that helps shows connectivity, because the rabbit, being a satellite polynomial, also has these bubble rays that you can use to find the path from the rabbit to the airplane. And then this component is a satellite bifurcation of the airplane. So of course that is connected to the airplane's hyperbolic component. So this is how we can find paths from in the mating locus using shared matings. Unfortunately, I don't have a lot of time in this talk to go more in depth about these shared matings, but I think it's maybe a through the looking glass at some point, you know. For higher peer n, I think peer 4 is very similar to peer 3. It's still genus 0. Oh yeah. So first, as a corollary, we just proved that a cylinder is connected, by the way. So just just want to mention that. Okay, but peer 4 is still genus 0. It's it has 4 punctures here, 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 and here, but it doesn't have any genus. It's mostly behaving like peer 3, where the ideas in peer 3 only have to be slightly updated to find all of your paths from all your different polynomials, but mostly it works out in just the same way. The only other thing to note, just for signposting for later, is that there's one special component of a 4 cycle, the basilica tuned with itself, that is also in the main molecule. So it's a bifurcation of a bifurcation. And this allows us to define the bubble rays as well. But defining bubble rays for maps like the airplane will be difficult, as I'll show in just one second. But just keep this picture in mind. So if that's peer 4, you can show that that one's connected with not too difficult. And then peer 5 is the first one that I think is really, really interesting. And we're probably not going to be able to get pictures for peer 6 and above, because just the genus of those just grow really, really too large. So in peer 5, there are 15 polynomial components that you need to connect up. And using these arrows, these are where I imagine the paths would be using just the combinatorial information. But you can see at some point, this path will have to spiral through some carpet mess in the bifurcation locus. The bifurcation locus in peer 5 and these higher components don't allow bubble rays as a technique, and we can't define veins so easily. I know a lot of people in this seminar are interested in carpets, and I think this is an interesting thing to think about saying, how can we define the image of a vein of the Mandelbrot set under the mating construction with a particular polynomial, like we saw in that Sherry Tom mating video, when they nestle into each other and form this Sierpinski-like looking curve, only sometimes instead of every component being a disk and a complement component, sometimes you'll have small Mandelbrot sets where disks are touching disks. But aside from that, it is like a carpet. And this question about whether or not then we can get from one hyperbolic component to the other could be answered by being able to find paths, like combinatorial paths in the Sierpinski carpet that would correspond to a vein. But you can see that there's a lot of structure here.
Sorry, Caroline, can you one more time say what the distinction between the different colored arrows are? What's green, yellow, and orange distinguishing?
Oh, yeah. So some of it was just getting a little messy if all of them were the same color. The colored arrows here all don't actually mean anything different. Okay, sorry. Good question. All of these things are, so the period 5 means that, but yeah, let me explain the labelings a little bit more, where 5 means this is the polynomial whose characteristic angle is determined by 5/31. In some sense, the number 5/31 uniquely determines a polynomial that lives right here. 31 is special because that's 2 to the 5 minus 1. And these are period 5 because when I do 2 to the 5 divided by this, I just get back the original number I started with. So everything here has denominator 2 to the 5. Is equal to blank over 31. So this is the polynomial component of 5/31. And the way to read this is to say that if I were to take 5/31 and mate it with 7/31, I would get right here. And that's the same thing as if I started with 27/31 and mated it with 15 over 31. So this is this example of a shared mating, which shows that the 5 over 31 hyperbolic component for this polynomial is actually in the same connected component as this 27 over 31's connected component. And as you can see, we find lots and lots and lots of shared matings. And the task for connectivity is to show that all of our polynomials are in the same connected component. So independent of whether the veins exist or not, I've been calling if you can find sufficient number of shared matings such that if the veins existed, pure N would be connected. I've been calling that combinatorial connectivity because there's really two different questions. One of them is a combinatorial question about whether or not you can whether or not you can find these paths to exist. And the other is this question of this analytic path about this analytic question about how you can actually find this path. But there can be alternate ways that don't require veins to still upgrade combinatorial connectivity to full-on connectivity. Okay, so then just a note on the current progress of how I've been working on this. This is just now for this.
So wait,
yeah.
Quick question. So I mean, is the conclusion then that your pure 5 is connected or not?
So the conclusion is that pure 5 is combinatorially connected. I have not found a way yet to connect. I can put all of them in the same component, except 14, as you can see, for instance, for 27 over 31 and 1 over 31, these are connected by some of these rabbits that you see. And then you can define the bubble rays for these rabbits to connect 1 to 27. So this tells you connectivity between these two hypercomponents, like full-on connectivity, not combinatorial connectivity. But we have this one component, 14 over 31, which is completely disjoint from these others. It's kind of floating around in this bifurcation locus. And this is the first instance of a phenomenon like this happening. And you can show in a not too difficult computation that as n grows asymptotically large, this is like the generic behavior of an arbitrary polynomial component floating around, that these rabbit guys are really sparse. These bubble rays are really sparse. So at some point, to really fully understand the combinatorial structure of the non-escaping set, you really need to understand how the veins embed in the non-escaping set. And I think, and if any of you would be interested in talking about that, I think that'd be really great. Right. So that's one of the difficulties that remains for the higher end curves. Of course, there are other ways that you could upgrade combinatorial connectivity to connectivity. But the current state of the progress that I have on this problem, I just wanted to mention, just as long as I'm talking about this, is saying that if these veins exist, or you have a weaker statement that would prove something that like this, and if in some sense the polynomial components are distributed randomly, then there has to exist a component that has at least 80% of polynomials in them. And this is just the shared matings that I can prove exist. You still have to think about, because they're not distributed randomly, you still have to show how they fit together. And that's sort of what we're working on right now. So, it's something for the generic case. Okay, but aside from that, you can also be interested in a cell structure, which I don't think I really have time for because I only have 12 minutes left. So I think I'm going to go ahead and skip this slide. Feel free to ask about it later. But this is a way to see about the genus of our surface. So the pure 5 curve has genus 1. You can see that through algebraic nonsense, through resolving singularities. But you can also see this by just literally computing an explicit cell structure. Or you can find a K33 in the combinatorial subgraph, but that's another thing. Let's see. There's also a question of effective models. Yeah. So essentially, this is this problem about bubble rays, upgrading them to the veins question. For two component in our Julia or Phil Julia set, this we can show corresponds to a capture, but then the external rays that land on this Julia set correspond to matings. So if you're going to have a reasonable model with the Julia set in your parameter space, the minimum structure you would hope to have is that when you can mate with an angle that lands on a Fatou component, which you could also capture with, that you want those associated hyperbolic components to be next to each other in actual parameter space. And this, you can work out the details, is true. It mostly boils down to setting things up and using parabolic implosion. But then the question that you might ask is what's more to want, and that's the question of veins, is that you really want to understand what the stick part of the Julia set does and how that winds around and combines with the veins in the Mandelbrot set. This part of Pier 3, I think, is believed to be a mating of a partial Mandelbrot set in a partial airplane, but it's done so in a carpety way that a lot of the techniques for Pier 2 just break down. They just don't work. And to show something like this, I think would be really, really cool. Because there's like, that's understanding like what if the Mandelbrot set were a Sierpinski carpet? That's kind of like this question right here. Okay, but then for the last 10 minutes, I want to tell you about this last project that was working on with Alex about these punctures. And for this, Alice is going to drink a little vial and she's going to get really, really, really small. And she's going to go into disappear into those punctures. And when she does that, she's going to learn some things about the parabolic structure. First is that Kiwi and Arfa developed machinery that's called rescaling limits, which I really don't have time to adequately explain where they came from in non-Archimedean dynamics. But what Kiwi did is he made all this machinery to describe how the degenerate behavior of rational maps when they degenerate to poles. And then Arfa took this and translated it from the world of non-Archimedean dynamics and showed that you can speak about this very well in terms of understanding periodic spheres in a tree of spheres. Now, why is that relevant? Well, if you remember from the obstructed mating slide that we saw 20 minutes ago, is that in P(n)0, all obstructed matings naturally have an association to a tree of spheres when we pinch down the Levy cycle. And then it becomes the question of understanding the periodic spheres when the map acts on this tree of spheres. So for instance, in the basilica example, this sphere mapped over here, and then this sphere mapped back. So if I just looked at the second iterate, that is a periodic sphere. And when I look at the second iterate, I just have a return map on a single sphere that I can get dynamics on. And then that dynamics is called the rescaling limit. And then also in P(n)0, you can show that all rescaling limits have to be matings with the cauliflower. So that's this parabolic fixed point element in the Mandelbrot set that kind of looks like this from the outside, but this is secretly a picture in Pier 2, where there's actually a periodic 2 cycle where there's this little nub that contains infinity maps to 1, and then 1 maps back to infinity. This is close to the puncture, and the closer we get, this guy is going to disappear, and you're going to have something that looks more and more like the actual cauliflower. So there's something going on here. In some sense, that puncture wants to be the cauliflower, which doesn't even live in our space. But we know then that because all punctures come from obstructed matings, that all punctures have a rescaling limit that makes them want to be something that's parabolic. So you would want to see some parabolic implosion around them. But the problem is that that notion doesn't even make sense because you have a pole in parabolic implosion. Although it is a purely local theory, it does not make sense when you have a pole. Just the machinery, just like when you're literally doing the work. And moreover, this is also made difficult because parabolic implosion is aided by the fact that you can work in coordinates for many. You have to work in coordinates around your parabolic, and it's locally just like z plus z squared. But for higher P(n)0 curves, because the genus grows so much, we don't have a way of even having coordinates for these these dynamical varieties. Okay, so what Alex Capiamba and I did is that we generalized the notion of classical parabolic implosion to a setting which contains the setting of P(n)0, and we show that we can account for this sort of mild pull. And in a generalization of parabolic implosion, which we call singular parabolic implosion, which is a purely local phenomena, just like parabolic implosion is. And then once we have this local picture where we say, okay, there's a cusp, that's what the local tells us. It just tells us that there's a cusp. We don't know what the global map around that is. So we still need to know the global combinatorics in order to understand what the neighborhood of our puncture will look like. And to understand that, it turns out to be enough to understand the rescaling limits at each of the punctures. So maybe the theorem is just that the punctures satisfy parabolic implosion, or maybe this would be a corollary, I don't know. But the way that I want to state it for this talk is saying that there's an asymptotic similarity between a neighborhood of a puncture in pure and zero and a neighborhood of a parabolic in a simpler curve. And sometimes you might have to have these pre-periodic curves. But this explains the fact that when Alice went down the rabbit hole, she saw elephants still because the punctures in peer 2.0 and peer 3.0 corresponding to the rabbits had the rescaling limit of just the cauliflower. So that tells us that the neighborhood in peer N0 around those punctures looks like the neighborhood around the cauliflower where you see these elephants. This can also show things like, so in peer 3.0 around the airplane's puncture, this is one where you have to use one of these pre-periodic varieties, and I'll explain on the next slide more precisely where that comes from. But this, another corollary of this implosion would be able to show that it's not, this picture is not just bad, but it's like inherently bad because the bifurcation locus becomes asymptotically dense as you get closer and closer to this puncture, because it is in the pre-periodic variety around its parabolic, and you have that local asymptotic similarity. So we know that, so this explains why every puncture looks like a cusp. And then the question is, locally, what does it look like? And then I can tell you how we can compute the global combinatorics. And for that, let's just let X be a puncture in peer N0, and that let's say that X is represented by an obstructed mating with this map F. Then, much like Tonley's mating theorem that says that the limb information of F determines the behavior of the puncture, if you look at a little bit finer information than just the limb, but you also look at what's called decoration structure, then this tells you what the global combinatorics of your rescaling limit is. And it breaks down into two cases. So if F is equal to a tuning of the rabbit with some other map, so it's in the space which I'll call just in the 1/2 limb. So the basilica square is the basilica bifurcation of the basilica. So there's an analogy between the basilica tuned with itself to the basilica as the basilica is to the main hyperbolic component. So this phenomena of tuning allows you to apply a self-similarity to the Mandelbrot set that if I started with any hyperbolic map, like such as the rabbit, so the basilica, then I can tune in any other map and get another map that's a tuning. And if F satisfies this formalism, then the rescaling limit, you just delete this rabbit when you take the qth iterate, and you just get this map G, and that G is our rescaling limit, which tells us our global combinatorics. In an example for what this looks like, and this is probably the best picture that we'll be able to have because peer 6.0 you probably can't draw pictures of. On the left-hand side, this is the puncture near the basilica squared, and you see all of the bubble rays, but you see 4 colors because there are period 4. And then on the right, you see peer 2.0, and this is not a puncture over here. This is the basilica mate the cauliflower. But you can see that asymptotically, they look almost identical, and that the deviations that you have from these additional bubble rays becomes less and less pronounced as you get closer to the puncture. The other behavior you can see is that if G is not a tuning of the rabbit, so if it's not in this region, then it's behind some dyadic tip. So for instance, the airplane lives right here, and it's behind the basilica tuned with the Chebyshev map z² - 2. And at that point, then the rescaling limit is the cauliflower mate that tip. And that's when we get these pre-periodic varieties for these maps that are far out in the Mandelbrot set. And that's what you see here. And that's why you don't see anything like elephants or anything that is reminiscent of any periodic variety, but you see something that is reminiscent of the pre-periodic dynamical variety peer 2.1. So on that note, we can remark that Alice can find her way home because no matter what peer n curve she is, she can always find the 1/n rabbit and then go down its rescaling limit back up to the main world. Thanks.
Okay, thank you. Let's thank Carolyn for a very animated talk. And let me start the discussion. So any comments or questions? Can we go back to the one of the first slides, you know, when you started talking about this connectivity?
Sure.
And let me ask a very naive question here, right? I mean, yeah, no, go further up.
This was the first slide on connectivity.
When you had these explicit iterations of your A and B.
Oh, on the very first
Yeah.
slide. Like here?
Yeah, exactly here, right? I mean, for this general n, and you should get some kind of polynomial, yeah, some polynomial equation between A and B, right?
Yeah, and this is what allows you to define this variety. That the variety is that relation of A's and B's that satisfy this.
Well, I mean, at least for a small n, I mean, you can compute this explicitly, right?
Mm-hmm.
And I mean, you should be able to check then whether it's irreducible or not.
Yeah, so people did that, and I think they only got as far as like n equals 4 or something. They really didn't get very far because you have to resolve all these singularities. Rohini's main insight was to say that you can reduce whether or not those polynomial expressions are irreducible to whether or not these Gleason polynomials are irreducible, and those Gleason polynomials are looking at periodic behaviors in peer 1. So if I were to look at this maybe like y0, y1, y2, all the way up to yn, the nth Gleason polynomial is any a such that yn minus 1, or that yn is equal to 0 as well. So that defines the Gleason polynomials, and those ones don't have any of these singularities to resolve, and it's much easier to compute. And that's what I believe some computations in Magma were done at Oklahoma State or University of Oklahoma. And that's how they were able to verify pure n is connected up to n equals 19. But at a certain point, you know, computers, like that's like a degree a million equation or something. And then it's just Eisenstein doesn't work. Like what are you going to do? I don't know. I'm imagining she has probably more progress by now. I don't know.
So I see. So I mean, these very naive techniques are just, you know, you run out of computational power very soon, I suppose.
Exactly, and I think that's why it's been like an open problem for like a couple decades now.
I see. I see. Are there other comments or questions?
Oh wait, let me show one more thing then.
Okay.
Okay, Pier 5 is a torus. Pier 5 is a torus, and you don't have to take my word for it, because you can print one. You can sew one up together. It's a torus.